So now we will move on to trig ratios, then we'll use that and apply it to finding exact values for some trigonometric functions, and then using that for related angles, and we'll use both the unit circle and the graphs to do so. So, let's consider something, say a problem like cosine of theta equals root 5 over 3, and then it's acute, and we say it's acute. And then we need to find sine theta, tan theta, and I'll chuck in cosine squared of theta. Why not? And I chuck in cosine squared of theta just so you know. Cosine squared of theta is equal to cosine theta times cosine theta. And that would just be 25. No, it wouldn't. That would just be 5 over 9. Now, going back to these ones. When we're thinking about a right-angled triangle, cosine theta is equal to adjacent over hypotenuse, right? So then we could say that the adjacent is root 5 and the hypotenuse is 3. And it doesn't matter really because if they really are, because remember, these things are called ratios, so it doesn't matter how big they each are as long as they've got the same ratio. And we know that they apparently have the ratio of root 5 to 3. So if we draw up our right-angled triangle, so this is our theta, and then this is root 5, and this is 3, we can use Pythagoras to get the opposite. So 9 minus 5 is 4. Opposite equals root 4, which is equal to 2. So then sine of theta, because it's opposite over adjacent, will be 2 over 3. And tan of theta, which is just opposite over adjacent, is just 2 over root 5. And if we want to rationalise the denominator, we multiply by root 5 over root 5, because that's just equal to 1. And we get 2 root 5 over 5. And now we'll look at two special cases of a triangle. Just for argument's sake, pretend this has got a length 1, this has got a length 1, and this has got it's an isosceles right-angled triangle, which means this will be 45 degrees, and this will be 45 degrees as well. So we need to figure out what this will be. So 1 squared plus 1 squared equals 2, and root 2 is root 2. And so, if we try to work out our sines, sine of 45 degrees, it's opposite over adjacent, so this opposite, and it doesn't matter which one we get really, 1 over root 2, and cosine of 45, because both base angles are equal, it will equal the same thing, because the opposite and the adjacent are the same. And then tan of 45, that's just 1 over 1. And then we'll rationalise denominator. So root 2 over 2 and root 2 over 2, that's equal to 1. Alright, and now let's think about the equilateral. So that's one set of exact values we can get for trig. Usually, as you probably understand, when you type something in on your calculator and do sine or cosine or something in it, it generally gives you something that just fills up the whole calculator with decimal places. These are special cases where it's exact. I'll do an equilateral triangle with side lengths of 2. Sorry guys, so that's 3, then this will make this root 3. And so now we can try and do the sine, cosine of 30 and 60. So let's do 60 first. Sine of 60 degrees, and this will be opposite, so the root 3 over the hypotenuse, which is 2. Then sine cos of 60, let's see, adjacent over hypotenuse, 1/2, that's good. And then tan of 60 degrees, opposite over adjacent, so it's root 3 over 1, which is just root 3. And then if we do for the 30, remember, this will now be the opposite, so that'll be 1/2 cos of 30 degrees. Oh, adjacent's this one, so it's root 3 over 2, and then tan of 30 degrees equals the opposite over the adjacent, so it's 1 over root 3, which is equal to root 3 over 3, if you rationalise the denominator. So those are some exact values for that. And so if we pull up a unit circle, and we can mark these in, we can say that sine of 30, this will be, well, so when this is 30 degrees, we'll have the coordinates, root 3 over 2, and 1/2. Then here, we'll have, if we look back to our cosine, our cosine and sine of 45 degrees, and then have a look at our 60. Yep. And obviously we can very easily tell on the 0 and the 90 this will be 1 and 0. And this here will be 0 and 1. And now hopefully you can notice that as you go from 90 to 0 for cosine, you get 0, 1/2, root 2 over 2, root 3 over 2, and 1. But then as you go from 0 to 90, the other way for sine, it goes 0, 1/2, root 2 over 2, root 3 over 2, and 1. So that way we can say that sine of theta, and we're talking acute stuff here, is equal to cosine of 90 degrees minus theta. Is that right? Yeah, I think so. Yep. And also, these are some exact values that you've got to remember. And if it helps, you could say this is root 1 over 2, and then 1 is actually root 4 over 2, because 2 over 2 is that, and then this one is simply root 0 over 2, and then as you go one way, you go 0, 1, 2, 3, 4, and keep doing the square root of that over 2, and, and it goes the reverse way for sine, with the same thing of root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, and root 4 over 2. Now let's think about expanding this into the whole thing. If we were to dash across here, we'd get coordinates, it would be the same height, so it'd be root 3 over 2 still, but it would be negative 1/2, wouldn't it? And we can keep doing the same thing here. Negative root 2 over 2, root 2 over 2. This would be negative root 3 over 2, 1/2. And then down here, it'd be, yes, 0, but it'd be negative 1. Now, I've cut out of the video a thing where I explain something that I actually think should just be saved for a later video. It's just a bit it confuses the content in this video, so just ignore it. Some writing will pop out about sine theta being equal to sine of 180 degrees minus theta. Just ignore it and just continue listening. If we continued all this, we'd notice that up here, both cosine and sine are positive. I'll write cos plus, sine plus to say it's positive. Over here, only the sine is positive, but then cosine is negative. And down here, both cosine is negative and sine is negative. And over here, cosine is positive and sine is negative. Now let's think about involving tangent in here. When we do this, tangents like that, but say we go over here, when we elongate it out here, because the tangent line is defined as being at x equals 1, we still have to do this like this. So otherwise, to make it elongate and meet, we have to go out at the other side. And so that tangent will become negative. So we can say that tan is negative here, and tan is positive here. And down here, something like this, when we elongate it out, we actually meet up here. So that's why tan will be positive here, and down here it's the same thing, tan's negative here. And so that's why you sometimes see ASTC stands for all positive, sine positive, tan positive, and cosine positive in the quadrants as you go anti-clockwise. Cambridge, I think in their textbook they say, all students trust Cambridge. Bit of self-glaze there, but if that works for you, then that's fine. So now we'll use this unit circle to look at the exact values for all the multiples of 30, all the multiples of 45. So let's start at 0, then 30, 45, 60, 90, 120, 150, 180, 135, and then 180. And we'll go all the way up to 360. 210, 240, 270. What's this? 225, 270, 315, 360, 300, 330. Now when you go, we know that the, let's work out sine for now, sine of theta. We know that this will be half, and this is root 3 over 2. And we know that this is root 2 over 2, and this is just 1 and 1. And that's 0 and 0. So now when we move to 120 degrees, this is in the second quadrant. So we'll know it'll be, we know the basic angle it'll make when we do 120 degrees, something like that. Basic angle would just be 180 minus 120, which is 60. And we know that in the second quadrant, sine's still positive, so we'd get that. And then we know if we did it another one, the basic angle would instead be 30, so we'd get a half. And at 180, it's flat on the x-axis, so the height will be 0. And then for 135, we know it will be the same as 45 degrees. And then this kind of just, it just does keep going. And then, so 210 here, the basic angle is only 30, but now it's minus, so it's minus half. Then for 240, will be minus 3 over 2, root 3 over 2, and then it'll be minus 1 at 270 because it's down like that. Then for 300, basic angle becomes 60 degrees. So that's root 3 over 2, and it's still minus. and then at 330 it'll be minus half, and then we'll be back to 0. And then at 315 it's just minus 2 root 2 over 2. At 270 we said it's already minus 1, and here it'll still be 2 root 2 over 2. Because it'd be like that. And now if we look at it for cosine of theta, and so if we then just keep on punching with this one, at 30, we'll fill in the acute ones we know. It starts with 1, and then it goes up to, well, we know it goes from 0 here, and then it goes up to half, then root 2 over 2, then root 3 over 2. And then we look at what it's like on the other side. We can see that it's the same for that basic angle, but negative. So, same for the same basic angle, but negative in that second quadrant. So, for this one it'll be negative half, because the basic angle it makes is 60 degrees. And then here it'll be root 2 over 2, so root 3 over 2, and then we'll be up to negative 1 and negative 1, that's negative, that's negative. And now we're going up to the third quadrant. It's still negative, but this time, and then the basic angle for 210 will be 30, so it'll be negative root 3 over 2, and this one will be negative root 2 over 2. The multiples of 45 are easy because it's only ever going to be root 2 over 2, positive or negative. Then 240, it'll go down to half, then this will be 0 and 0, because it's just right on the y-axis. All the points will be on the y-axis. And then 300, this is when it starts to get positive again. And so 300, that's 60 degrees away from the x-axis, so that's going to be a root 3 over 2. 315, root 2 over 2. 30, that will just be half, and this will be 1 and 1, I think. See, 300 will be 60 degrees away, meaning it'll be half, then that, and then that. Alright? Yep. And obviously we could convert all of these to radians. That would be 0. This would be pi over 6. This would be pi over 4. This would be pi over 3. And this would be pi over 2. This would be 2 pi over 3. This would be 3 pi over 4. This would be 5 pi over 6, and this would be pi. And then we'd have 7 pi over 6, 4 pi over 3, and 3 pi over 2. And this one would be 5 pi over 4. This one here would be 7 pi over 4, I think, yeah. And this one would be 5 pi over 3. This one here would be 11 pi over 6, and then this will be 2 pi. Now for tan, if we go over the values for tan, remember that in quadrant, it's quadrant 1, it goes for 0, 40, 30, 45, 60, 90. It goes 0, root 3 over 3, 1, root, then root 3 for 60, and then it goes up to infinity. It's undefined. And then it starts being negative. So it goes 1 to 20, negative root 3, (135), negative 1, 1, 50 is negative root 3 over 3, 180 would be going down going up to 0, then 210. That's when tangent becomes positive again. So we start at positive root 3 over 3 and then go all the way up to undefined. That would be at 270 degrees. And then we start to come back down again to 360 degrees, which is at 0. I'll go into more about like when you're inversing trig and trying to find solutions to equations. That's when the graph is probably more relevant, but here the unit circle still works very well.